Okay, so this is a sort of wrap-up of the nonlinear dimensionality reduction methods. We will see some applications of these methods. Usually, I mean, the step zero, the ground zero is not the easiest application is, okay, I take the data, I run the algorithm, and I look at the result. Okay, so visualization of the data. This is what we have already, in a sense, done in a previous lecture. But that's only the first step. Now, we usually want to employ these algorithms in a manifold learning workflow. So, for example, in classifying the content of images and videos, which was the first ever application of these algorithms, in the papers about that introduced ISOMAP and LLE, the examples were the low-dimensional embeddings of handwritten digits, or I didn't show you these, but another example was rendered faces, so synthetic faces, with different angles and inclinations, and they were classified in terms of rotation and inclination. In videos, so usually this is what we want is to train our algorithm on some known set of data in order to label them, and then to use it on some unknown data and apply these labels it learned from the training set. For example, for videos, one can classify frames, so run our algorithms on the frames of the video, and use the parameter space that ISOMAP, LLE, whatever create in order to compute distances between frames and produce summaries of the video or compression algorithms for the video using these distance instead of the frame number for proximity. It worked. Now, for example, face recognition. NLDR and ISOMAP were successfully applied to two databases of faces, which are the same face with different angles, expressions, light expositions. So, for example, this is a sample from the ORL database, which is the Olivetti database. So you see it's the same face with different angles, so different linings, and different expressions. You want to train your algorithm to classify faces just based on whose face is that, and not on the expression of the face. So you train on these, you train them on this, so the algorithm should label all these 5 faces with the same label, all these 5 faces with the same label, etc. And you train them on this dataset, and then you use a similar input data and see if you can manage to classify the faces. Now, if you think about applying some algorithm to this situation, there is almost immediately a problem. These algorithms work at best when your data lies on some flat manifold, something which is a piece of Euclidean space twisted and rolled up in higher dimensions, not if something closes up. Now, we don't have any assurance of the fact that the faces manifold is something like that. So we should be prepared to deal with the situation where our manifold is not globally Euclidean, just in a really high dimensional embedding. Moreover, what we want to do is not only to visualize and parameterize our manifold, but we also want to implement a decision algorithm. So we are given a new point, and we should decide to which point it's closest. So we want to divide our manifold in pieces, and each piece is determined by some training points that lie there, and or worse, we are given our training data set, and so we know when 2 points are the same, in some sense are close or not. Not in the differential geometric sense, in our classification problem sense, if they have the same label or not. Now we are given 2 more points, and we want to say if they have the same, if they should have the same label or not. We don't know what label is this, but we would like to know if they are close enough or not. So the whole point is we want to project new points in our parameterization. So a way to do that is the nearest manifold algorithm or approach. The authors used a variation of the LLE method to find charts of the manifold. So we don't use the LLE globally, but just locally on the manifold. And these charts are given as simplices in R to the D, so triangles in the plane, for example, or tetrahedron in the space, tetrahedra in the space. Why? Well, because LLE writes everything as a combination of the nearby points. So if we use it to produce charts, we will produce charts which are convex combinations of nearby points, which is simplices. Given a new point, y, we project it on each chart, so on each simplex, and we compute the feature coordinates of the projections. Now, these feature coordinates are written as combinations of the coordinates of the vertices of the simplex, so barycentric coordinates, if you know them. And these coordinates, like, think of a triangle in the plane. So you have your triangle given by your 3 points. Now you have different situations for a point here, for a point, let's say, here, and for a point here. So the blue one has all positive coordinates, so it's in the convex combination of the 3 points, of the 3 vertices. The red one has 1 negative and 2 positive coordinates, and the green one has 2 negative and 1 positive coordinates. Now, these correspond to 3 different situations and 3 different ways of computing distances of the point from the chart, because we want to say how far the point is from the chart and which is the best projection in the end. So we want to compare the projections of the points on the various charts we obtained and see which is the closest in a meaningful way, not in the Euclidean way of the high-dimensional embedding. So depending on the coefficients, meaning depending on these 3 situations which I mean, if your data is two-dimensional, if your data is d-dimensional, there will be more. Depending on the coefficients, you define a distance, and then you just compute the smallest distance, and you select that simplex. Now, this gives a way to work in local coordinates for adding a new point to your space. So you have a new point, a new data point, you find the closest simplex, and then you work in the coordinates of that simplex. You project on that simplex and work there. Whatever you have to do, if you have to compare this new point with your known ones to see if it belongs to some known label, or if you have to compare this point and another new point to see if they're close enough or not, and so on. So this is an example of actually supervised manifold learning. Another big category of examples. I mean, this is not only the previous one was not only for face recognition. There are countless other examples. For example, the video stuff I talked about. Another interesting example is tracking and pose estimation. Okay, this sentence doesn't mean anything in English, but one of the successful applications of NLDR algorithms is object tracking. So you have an object and you want to track the movements of your object. Usually, by just tracking the silhouette, the contour of your object. So you have two-dimensional pictures of it. And you applied some image filter to draw out the contour of your, or you applied the gradient descent we talked about some lectures ago to get the contour of your object. And now you have your contour, which is a curve in the plane or an intensity map from the square or whatever it is. So it's something which is usually high dimensional that gives you the shape of the 2D shape of your object. Now you want to apply dimensionality reduction to learn latent variables in your representations, which are usually labeled in some way, like as joint locations or silhouettes or contours or whatever. And then you want to compute again these latent variables on a new image and find the label that they correspond to. For example, you may want to track faces in presence of large rotations or occlusions of the visual, or to recognize activities, so operations done by your object, which could be a human, for example, from just silhouette, reconstructing the whole 3D pose just from the contour image. So this is not always possible, obviously, and this is not possible without context. But if you know, for example, that your silhouette is a human silhouette, then chances are that if you train your algorithm properly, you can get the fully reconstructed 3D pose from just the contour image, from just the silhouette. So this is what are called activity manifolds. So we have silhouettes of people walking from different camera angles, which gives us what are called view manifolds, so the rear view, the front view, the side view, whatever are, in a very high dimensional space because it's a space of silhouettes. So black and white images which draw the contour of the human shape walking. Now, an activity manifold is usually a path, so a one-dimensional manifold inside this view, well, not one for each view manifold. So, and they are all coupled together. So it's the same activity in each view. So, for example, you have someone walking in a circle, and you have the rear view, the front view, the side view. So this walk gives you a path in all of these view manifolds, and this is your activity manifold. And obviously, someone walking, it's a very complex movement, but if he's walking in some regular fashion, like he's normally walking along a path, the movement will not be changing too much. I mean, the human eye will see a regularity, a pattern, a clear pattern in this movement. So we want to train our algorithm to see the same kind of thing. So if you just see from the side the silhouette of someone walking, you can imagine all the movements that its joints are doing while he's walking, his knees and hips and whatever. So we want to do the same thing. So part of the problem here is to keep track of the parameterization map and its inverse. So we want to be able to go from the view manifold to the latent variable space of the activity manifold, and then to go back. Now, this is an example taken for an actual case. So you have the silhouettes of the people walking, and you have these, well, this is a 3D curve, so it's not really crossing here, but anyway, it's like more something like this. So it's not crossing, it's whatever. And there are some still frames for each, from each point. Obviously, this is a path. You can, I think you can clearly see that it's not a line, and that's single line, and that's because the person was filmed walking for quite a time. So the cycle of movements he would do in, let's say, one full step, which is the basic repeating pattern, were done several times with slight variations, obviously. So you don't really, I mean, you're not an automaton, so you don't exactly walk every step in the same way, but quite close. Obviously, this is a path also in the high-dimensional space of black and white images, which has a lot more dimensions, so it's not so easily recognizable. So this is, and this is this, obviously, as you can see, the side view, one of the side views. I mean, obviously, you can have side views with an angle. Now there are, for example, just to here, in this part here, this is the part of the step where you are sending one leg forward and the two legs find themselves more or less aligned with the side view. So this is a partial occlusion problem, because at that point you see one leg. So there is a part of the body you don't see moving in the silhouette, and but you should be able to infer the movements also of those joints which you cannot see. So this is not, I mean, it may sound trivial because your mind does that almost automatically, but it's not. So just from the data you see here, you should understand that there is another leg which is behind the one you see, and that leg is moving forward and in some way. So obviously this is obtained in your mind and also by your eye, just for the continuity of movements, because you know how the movement is supposed to look, and so you can imagine what is happening behind the other leg. But I mean, that's a problem in this situation. That's something your algorithm should be able to deal with. So there are three main components which are all quite technical to develop. So you have to learn three things. You have to learn the manifold, so you want a low-dimensional embedding that preserves some geometric structure, I mean the usual. Then you want to learn the mapping manifold to input, not the parameterization, which is given to you by the step one, the first component you learned. You want the inverse mapping. So you want to solve an inverse problem, which is an interpolation, a nonlinear interpolation problem, which can be very difficult. Luckily, depending on which algorithm you use in the first step, you can have some closed forms in the second one. So that helps. For the known points, then you obviously anyway have to interpolate for all the other points because you want to be able, I mean, in principle, you would like to draw a line in your parameter space, get back to the manifold, to the view manifolds, and then estimate the pose, the 3D pose. And now there's a third step because the third component you want is something that maps from the view manifold to the pose manifold, which is a linear mapping from the embedding space, which is the space of silhouettes, blah, 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 to the 3D body pose space. So the space of parameters that specify the position of the human body, in this case, in the three-dimensional space. Nope. By the way, this is not, I mean, the human walking obviously is not the only field of application of this kind of framework. Also face recognition, as I told you before, and some cyclic, rhythmic, periodic movements like walking, which are, I mean, natural movements which are almost periodic. I mean, not really periodic, but you perceive them as movement patterns which are repeating. Birds flying and stuff like that. And also to medical images, which is the next application. So I won't be talking too much about this, but think about some imaging technique applied to the heart or to the pulmonary system, so to the lungs, the blood flow or anything like that. You have many images, so the frames of a video, you would like to say, so the MRI of the heart at every whatever fraction of seconds. The overall motion is periodic in the nature way. So, I mean, there's a pattern. It's not exactly periodic, but it's almost like that. Like someone walking, birds flying in circle and stuff like that. The heart pumping the blood through the body. And you don't have too many degrees of freedom. Like, think of the heart beating. I mean, there are like, I mean, depending on how accurate you want the description, but there are two phases, and for each phase you have contraction and dilation. So, in principle, you could use 4, 6 variables to describe everything. I mean, in your mind, as degrees of freedom, not as actual visual, I mean, variables from the image, but as degrees of freedom, you could think of, you end up with 4, maybe 6 if you're really imaginative or knowledgeable in medicine. I don't know, I read that you could imagine 6, I don't know what they were talking about. But each change in this degrees of freedom causes a no-rigid deformation of the image, which is a complex image transformation. So a It's not like when you're classifying head positions and your transformation is the 3D rotation of the head, which, I mean, is a complex image transformation, but not that much, because it's the two-dimensional projection of a rigid movement in 3 dimensions. Think again of the heart beating. Obviously, the systolic and diastolic compression and dilation are easy to explain, but if you think of them as changes of the MRI image of the heart, they are very, very complex. Or even worse, if you account also for the blood flowing through the heart. Now, also, this is a usual feature of these situations, the latent space, so the space of features, the space of degrees of freedom, is quite close to being uniformly sampled. Because it's a rhythmical, it's a periodic behavior, so if you sample in time the images, you get something which should be uniformly sampled also on the latent space. Now, parameterizing images via some NLDR algorithm and using the learned parameters to reorder the images gives you minimal changes from one image to the other. So this is not the time order in which they happen, but it's the order in which they change less. This helps to, for example, to compare different time series. And this helps to compute deformations from one image to the next in this order, which are easily extended to global deformations of the time series with small of the parameter space with small with suitable estimates, let's say. And I won't be going too much into this, but there is also a lot of just because the images of these are less I mean, I couldn't write anything that I couldn't find any accessible database of medical images to write some code and show you the results, but anyway. Now, the last application I would like to sketch is text processing. And this is a mixed application because we will apply the idea from the last dimensional reduction technique we saw, so the heat kernel, to information geometry. So text classification usually is based just on single words and not on the order. So also humans can tell you at a very high level what a text is about, just looking at all the words used there instead of reading sentences. So if you just know the words that are in the document, usually you can guess what the document is about. Or if you're given some bins, you can usually tell in which bin the document belongs to. Usually text you want to classify are modeled as draws from a fixed multinomial distribution. So n-grams. So the space of, so you're working on the statistical manifold given by multinomial distributions with its Fisher metric. The nice thing is that this statistical manifold can be embedded as a domain inside the unit sphere of some high-dimensional space. So your statistical manifold is just a piece of unit sphere, not two-dimensional sphere, some d-dimensional sphere. And the round metric is isometric to the Fisher metric. So the metric of the sphere is the one you want. So this makes it very easy to do computations, and also gives you curvature bounds, because the curvature of the sphere is the constant positive curvature, 1 over the radius. So 1, well, there is a constant. Anyway, bounded positive curvature. In text classification, there is a widespread use of kernels to put weights on this Euclidean representation in order to establish decision boundaries. So you want, for example, you are given web pages from the site of the Polytechnical. So the personal pages. And so you get student pages, they are not here, but you could, teaching staff pages, administrative staff pages, and research group pages, let's say. These 4 kinds of pages. Now, I give you one page, and I ask you, okay, this web page, what type does it belong? And you can look at the distribution of words inside this page and compare it to the known ones that you have already labeled to see to which it's closer. Now, what does it mean closer? Well, it means that you want to draw on your manifold some boundaries that enclose the pieces where, so for example, if you have only 2 categories, you want to draw something between these 2 categories, and what's left and what's right are in one and the other bin. Obviously, then the problem is what happens if you just hit a point on the boundary. This is another question. Obviously, these decision boundaries need some distance. And one nice distance used is the diffusion distance of some diffusion process. Now, the heat process usually is very fine for these. One problem is that in these kind of applications, you want estimates on eigenvalues. So you want to estimate how small or big the eigenvalues of your Laplacian are in order to get estimates on likelihood and stuff like that. And this is where you could do all the kernel stuff without the manifold structure. These are known as Mercier kernel, I think. Mercier kernels, I think. And these are just on the Euclidean coordinates of your of the parameters of your multinomial distributions. The first problem you could see there is that these kernels are usually applied ad hoc to your data before working with them. So you don't exactly know how you should choose the parameters for your distributions and how you should put weights on them. I mean, there are some rules, as far as I understand, these are thumb rules, but there is not a given procedure. If you use this geometrical interpretation, you can find some ratio behind these choices, and you have a family of kernels which are derived from the heat kernel, for which you have a geometrical interpretation. Now here, this fact that you can obtain your statistical manifold as a piece of the sphere is very useful, because once you have curvature bounds, you have bounds on the eigenvalues of the Laplacian and hence on the partition function of the heat kernel. So it turned out to be a winning choice to apply the heat kernel to these kind of problems. Why? Well, it's the natural generalization of the Gaussian kernel in the Euclidean space, so which is what the Mercier kernels are based on. It has a nice approximation, which is called parametric construction. I mean, it's something related to all the diffusion semigroups. You can write down a function called parametrics, which can be, in this case, I mean, computing the kernel for that manifold is not easy. It's not, there is no closed form. I mean, no accessible closed form. But you can write down easily approximations to the order you want using this parametric construction, which is known for the, in this case, for the sphere. So to compute the heat kernel, you need to use the piece of the sphere you're working on. But for the parametric, you just use the sphere, so it's much better. And thirdly, you have bounds on the spectrum of the heat operator, so of the Laplacian, in terms of the curvature. And given that you're in the sphere, the curvature is constant and positive, and you have every bound you may want. So the idea here is, again, to supervise learning. So you give some training data set where you label the text document depending on the content, and then you ask your algorithm to understand new documents, to classify new documents depending on the labels you already given to it. Now, the idea behind it is that you are somehow drawing words randomly with a given distribution and putting them in your document. I mean, it's not how usually how you write documents. It's how some people write documents, not always. And but then what happens here? It means that you have given some probability to the words in the dictionary, and you are drawing according to that probability. Now, you take the manifold of all probabilities of this kind, which is the multinomial distributions manifold, and you would like to divide it into pieces, and each piece, each different distribution of probabilities on words corresponds to a different subject for your document. Now, using a diffusion kernel from, even for example, you have 2 points, one is labeled A and one is 2 distributions, one is labeled A and one is labeled B, and you want to divide them, you can compute the heat kernel and the diffusion distance from A and from B, and just draw the line. Now, this can give quite different results from just the Gaussian kernel in the Euclidean setting. Think, for example, if you just use the normal distributions with mean, mu, and standard deviation sigma, this corresponds to what? Well, if you are on R, or on Rn, is just Rn to the -1. So the choice, all the possible choices for mu, the mean, times the positive numbers. Now, the Fisher metric on here, you can show it's just the Euclidean metric over sigma squared. So this is the so-called hyperbolic metric. So in 2 variables is the hyperbolic metric on the upper half plane. And let's say this is Rn minus 1, this is R greater than 0. So you want to separate your 2 points. If you use a Euclidean setting with the Gaussian kernel, you will get the separation between these two parameter points to be just the, well, it goes on here, just the midline between them. But if you, nope. If you use the Fisher metric and the heat kernel, the associated heat kernel, because here you're using the heat kernel just of the flat Euclidean metric. But with the Fisher metric, you get a geodesic of the hyperbolic plane, which is actually a half circle which is orthogonal to the x-axis, which is a much smaller decision region. I mean, the region here and the region here are quite different. So it gives you quite different results in terms of classification. And if you want to think about the statistical meaning of these, think that as you're going down, the variance is going to 0. So as the variance gets smaller, you need just a smaller control, a tighter control on the mean. Okay. Anyway. So this is what happens with the Gaussian kernel in the flat case. This is what happens with the heat kernel of the Fisher metric. So you see that this gives you quite different decision boundaries. So anyway, this is we saw 4 fields of applications of this technique, all in the way of manifold learning. So we want to learn the manifold and then be able to draw conclusions. This usually happens as a supervised learning. There are also applications which are entangled with neural networks and stuff like that, which are more advanced, but we are not digging into them. Everything we talked about is at least 10 years old, I think. So quite old for the computer science and data analysis part. And I think it's enough.